Alright, this is a video on Dalton's atomic theory. Um, this blue sphere that is on the screen right here is a model of Dalton's atom. This is not the current or the modern atomic structure. We are slowly going to build up to what the modern atom looks like. But for right now, we're going to start with Dalton, who is in many cases considered to be a founding father in the world of chemistry. His work, Dalton's work, started off about 2,000 years prior to Dalton's birth with this man, Democritus, a Greek philosopher. Now, Democritus was the first to coin the term atom, and he actually was the first to describe atoms as pretty much everything. If it's not atoms, then it's nothing, or it's empty space. So, considering that this is, 500 BC, that's quite remarkable considering that most ideas of the existence were religion-based, not necessarily science-based. And in his case, I can't really say it's science-based because he did not use the scientific method in order to come up with his ideas. Those ideas being that atoms are indestructible and atoms are indivisible. So the shortcomings with Democritus is, one, he didn't have any, because no scientific method, he did not have any experimentation to refute any of his claims. And the other thing was he had no explanation as to chemical reactions. So just because he mentioned that atoms are indivisible and atoms are indestructible, that didn't really address the chemical reaction aspect of it. So during chemical processes, he had no explanation for that. So no explanation for chemical processes, and he had no experimentation to back up his claims. Those were his two shortcomings. Now, fast forward a couple thousand years, we come across John Dalton, who was an English school teacher and chemist, and he came up with 5 postulates of an atomic theory. Now, his theory was pulled out of mainly experimentation with looking at different elements of compounds and kind of looking at their ratios. Now, Dalton did more than just these 5 postulates of this theory. He also is responsible for gas laws and a handful of other laws. But right now we're going to focus on the atomic theory. So, one, elements are made of tiny particles called atoms. Now, this is pretty much the same thing that Democritus said. However, there was no idea of elements in Democritus' time. It was, the elements were like, I'm not saying that he suggested this, but back in those days, elements were like fire and water and earth and wind, and those were the considered elements. But the modern idea of what elements are, like on the periodic table, Dalton was using that current knowledge to decide that elements are made of tiny particles called atoms. So 2 and 3, you'll actually see these two things written in some cases right with each other. Your textbook actually splits them up. So all atoms are given element are identical, meaning every atom of hydrogen that ever existed is all the same. It's all the same, looks the same, mass is the same, takes the same amount of space, everything. So they're identical. 3, atoms of a given element are different from those of any other element. So looking at an atom of hydrogen, it is different than an atom of fluorine, okay, which can make sense. Number 4, atoms of one element can combine with the atoms of other elements to form compounds. Now, a given compound always has the same relative number and type of atoms. So, for example, if I'm making water, water is made up of 2 hydrogens and 1 oxygen. So when I look at one sample of water on one side of the planet and then another sample of water on the other side of the planet, or in space or wherever, it's always going to be 2 hydrogens and 1 oxygen atom. So that's going to be something fixed, and that actually led to another one of his laws, which we'll get to at another time. But atoms of one element can combine with atoms of other elements to form compounds. Okay? Now, 5, atoms are indivisible in chemical processes, which means they cannot be split. That is, atoms are not simply created or destroyed in chemical reactions, they are changed the way atoms are grouped together. So, an example, here I have in the first quadrant, we have atoms of element A, and we have 10 of them, 10 atoms of element A, and we're going to go ahead and call that element H. And then atoms of element B in the second quadrant is O. Now, if I just mix the two elements like I do in quadrant C, okay, quadrant number 3, if I was to just mix them, that's not changing what they are. They're just a mixture of elements A and B. But if I can chemically combine them like I do in the fourth quadrant, then they become something different than their original elements. Okay? Now you notice that I had, okay, let's go ahead and count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I had 10 hydrogens, and I had 1, 2, 3, 4, 5 oxygens. Okay? Now if you look here, there's 2 hydrogens and 1 oxygen. Okay, remember, A equals hydrogen and B equals oxygen. Okay? You'll notice that I still have the same number of atoms, it's just I've changed the way that they've combined and the way they react with each other, or the way they react with their environment now, because they are not just the elements, they are now a compound, and that compound is distinctly different from the atoms that make it up. Okay? If you guys have any questions, ask.